John Taylor distortion. In 1937, Jahn and Taylor proposed a theorem which states that any nonlinear molecular system in a degenerate electronic state will be unstable and will undergo some kind of distortion which will lower its symmetry and energy and split the degenerate state. For example, if we take example of copper 2 positive, which is a T9 system, here we see that T2G is filled with 6 electron and EG is filled with 3 electron. There is a possibility of two equivalent energy states. These two equivalent energy state might be there is 2 electron in dx square minus y square and 1 electron in dz square, and the second is the 1 electron is dx square minus y square and 2 electron in dz square. Both are energy equivalents. These are degenerate states. The electronic states of the copper 2 positive ion is doubly degenerate, and according to John Taylor theorem, this state can't be stable. This is not a stable state. Therefore, the regular octahedron will distort in such a way that the two states will become unequal energy states. First case, if the actual configuration is the Eg orbital is dx square minus square having 2 electrons and dz square having 1 electron, then the ligands in xy plane will be repelled more than the ligands along z-axis. Since the ligands in xy plane move further away, the dx square minus y square orbitals becomes more stable than the dz square orbitals, thus destroying the degeneracy as shown below. Eg will destroy its degeneracy, and there are two energy states, that is dx square minus y square having 2 electron lower energy state, and dz square with 1 electron is the higher energy state. This is the case of Z in case, that is the ligands along z axis will move inward and the ligands along xy plane will move outward. Second case, if the actual configuration is the other one, that is the 1 electron in dx square minus y square and 2 electrons in dz square, a distortion of opposite type results. That is, now the case will be revert. The ligands along z-axis are repelled to a greater extent than the ligands in the xy plane. Since the ligands along the z-axis move away, the dz square orbitals becomes more stable than the dx square minus y square orbitals. Thus the degeneracy is removed as shown below. And here the Eg will split into two degenerate energy levels, where the dz square will be the lower energy state with 2 electron and dx square minus y square will be the higher energy state with 1 electron. This will be the case of Z out, that is the ligands along the Z axis will move outward and the ligands along the XY plane will move inward. It is difficult to predict which situation actually occurs, that is the first case will occur or the second case will occur. This cannot be predicted which will be the more stable case. So elongation of two bonds along z-axis is energetically more favorable than elongation of four bonds in the xy plane. You know, along the z-axis there are only two ligands, while along xy plane there are four ligands. So energetically it is favorable that elongation of two bond is easy process, as the z out case is the more common that than z in. Now we will see that Cu2 positive, that is CuF2, CuCl2, CuCr2. Here the Z out case is shown in figure. Unsymmetrical electronic configuration in the EZ orbital is expected to show this type of distortion with the unsymmetrical electron configuration in EZ. That is, when EZ is unsymmetrical field, there is a possibility of John Taylor distortion. There's also a possibility of John Taylor distortion in T2G when it is unsymmetrically filled. That is, T2G is unsymmetrically filled. There will also be John Taylor distortion, but it's a very low extent. It is negligible. So John Taylor distortion is only shown by easy unsymmetrical. because there is the extent which is we can determine, we can expect to be high, and a similar but smaller effect is to be expected when T2Z are unsymmetrically filled. Since T2G orbitals are not directly pointing toward the ligand. See, T2G orbitals are not directly pointing toward the ligands in an octahedral complex. So there is a very low value of Jahn-Taylor distortion. Always remember, Jahn-Taylor distortion is shown by the complexes compounded in which the central metal ion have unsymmetrically filled EG orbitals. This is the primary condition for Jahn-Taylor distortion, that the EG orbital should be unsymmetrically filled. So let us now see consequences of Jahn-Taylor distortion. Six coordinated complexes are found to possess distorted structure. You will see that six coordination complexes are possess distorted structures. The distortion, why this distortion occur? This distortions occur due to the Jahn-Taylor distortion, Jahn-Taylor effect. For near H2 and too far H2 due to Jahn-Taylor distortion. We will see that the four ligands. Now we will see the stability of copper complex with two ethylene diamine ligands and two water ligands, and we compare the stability of this complex with a copper complex where the three ethylene diamine ligands are attached with copper. So when compare the stability of both these two complexes, so we will find that the first one is more stable than the second. The reason behind this, if we see that if we see simply the chelation effect, the second one should be more stable, but the first one is more stable. Why? Jahn-Taylor distortion will explain this effect. How it will explain? This is because in the later two EN chelates ligands make use of two elongated bonds due to Z out along Z axis. Their rings are under strain and thus less stable. You can see that when there are three EN, that is ethylene diamine ligands are there, you will see that the two rings will have strain due to Z out elongation, and this Z out elongation is not a case in the first one where the two water molecules are along the two Z out sides and the two ethylene diamine are along the XY plane. So the stability is explained by Jahn-Taylor distortion. The next one is the adsorption spectra. When we compare the adsorption spectra of two compounds, one having no Jahn-Taylor distortion and one having Jahn-Taylor distortion, we earlier see that Jahn-Taylor distortion is a type of loss of degeneracy. So when degeneracy is lost, there is more possibility of transitions and the single peak spectra split into a double peak spectrum. This can only be explained by the loss of degeneracy, by the loss of symmetry, and thus we can see that this splition of spectra is explained by Jahn-Taylor distortion. The next one is the reactivity of complexes. The Jahn-Taylor effect also explains the reactivity of complexes. For example, copper complex, that is copper complex of water is acting as a ligand, there is a possibility of exchange of two of its water molecule on the elongated axis more rapidly than the four water molecules in the XY plane. So this is also explained by Jahn-Taylor distortion because the elongated water ligands are more prone to get exchanged. So this is all about Jahn-Taylor distortion. Thank you.